Good evening already, right? To all of you, we are here in the Valdaura Labs. We have just finished the review of the Master in Advanced Ecological Buildings and Biocities. We have as guest critic José Toral, who will give us a lecture now on his work. José is a partner together with Marta Peris of Peris and Toral Architects, and they are both professors at the university, and they have amazing projects, most of them residential, public residential buildings in Barcelona, Palma de Mallorca, and Ibiza. And they have also been doing other public buildings in Barcelona as well. He has joined us for the review, and I will not spend much time, more time introducing him. So please welcome José Toral.
Okay. Thank you, Guillermo. Thank you, Vicente, for inviting us. Well, I named the lecture Form Follows Material because I will talk about some projects, and each one of them, there is a main material that is the one that is shaping the form of it. So for us, this is a way of thinking that it answers very well to our times. So, but to begin, I will begin with this idea of the sustainability. To talk about sustainability, there are like three items that for us are very important: the environmental issues, the economical ones, the sustainability, economical sustainability, and finally the social sustainability. But for us, architecture has to be able to answer to all of them, not only to the environmental one, not only for the social one. It's just the combination of all of them. So this is a scheme that we like to show of our work, and the lecture will talk about this. So the important thing is to understand how to approach to environmental sustainability and to social sustainability and to the economical one, not just like facing them on one decision. So we think that when we combine two of them, so if you combine the environmental issues with the social issues, you can take some strategies like using the intermediate spaces, increasing them in order to make some green gardens, some atriums, some patios, some strategies that environmentally will work very well, but also will have a social feedback. And also with all of the combinations, so we combine the environmental with economical, the strategy we think it's the best is the idea of reducing. So when you use less amount of material, you use less amount of layers, you're able to be more sustainable, but also you're able to be more economic. And finally, to be more economic and social, we think that the best strategy is the idea of sharing. When you share everything, you use one, you just build one and many people use it. So you need less amount of energy. So, and you need less amount of money, it's more economic, but also you have a social feedback. So you have these spaces. So I will go through these concepts, just looking at some of our projects, just to understand these ideas. Okay, we'll begin with this point of the intermediate spaces, the environmental and the social sustainability. Okay, I will begin with this project of Ibiza. It's 43 social housing. And the main goal of this project was to be able to make a building with no active system. There's no heating, there's no cooling, but then which are the parameters that we can use to have this comfort. So we have humidity, temperature, we have the movement of the air, we have the clothing, the metabolism of the people, and also we have the radiation, the heat radiation. So in some moment we can translate these parameters into some elements in architecture, green gardens, cross ventilation, hygroscopicity. And the other thing is here we have the abacus, the Carrier psychometric abacus. Carrier is the inventor of the air conditioner, and he told us that everything that was outside this green area, you should put on his machine. But as we want not to use his machine, we will want to work with the parameters that we know we have in order to be able to solve the problem. And I like to explain that this is our site drawing. So the site, it's the climatic card. So this is something that we take a lot in consideration in the office. So, and we not only look of one chart. So in this case, the humidity, the relative humidity, the one of the regulations is not true at all. In the Balearic Island, we have a very high humidity in summer. So we don't take only the one of the Código Técnico. We take more the one of the airport, the real data, and and we begin the project analyzing this climatic chart. So one of the main problems is the summer. We have very humid summers in the islands. We are surrounded by the sea with many waters. So normally we have this over 80% humidity, and the ideal humidity is it has to be around 50 and 60. So if we are lower, it's too dry, and if we don't have defenses, and if it's too humid, there's many bacteria that are increasing. So in order to be able to put the humidity at the level that we needed, what we did is we choose as material the earth block. So we wanted to build with earth because the earth has the ability to make the humidity regulation. So we like to show this diagram. This is some drawings we did in the competitions, because in this drawing you don't see the limits of the building, and this is something that is very important to us. The building, it has a shape, but this shape, it's only the moment that we stop it, but we build it. But the important thing is that it's more a system than a shape, and it's a system made of equal rooms. All the rooms measure the same. They all have 3 by 4, so 12 square meter, and we use the same room in order to make the living, the kitchen with the dining, and all the rooms, and also the stairs, and also the patio, and also the room where everybody enters. And then we have some middle modules. Okay, and the system, it's these rooms, the building, it's emptying when you go upper, so you have less amount of rooms, and we are shaping the building in order to have more vertex, because each vertex is a vortex and generates more movement of the air, and it's something that will help us in order to generate and the other thing is that we wanted all the houses to face south, and in order to do that, we needed to go to the upper level, and the upper level, the atticos, they should be one step back, and using this idea, all this step back, it's integrated into the volumetrics of the building. Seeing the plan, we have 3 staircases. So each staircase has the stair, you have the lift, then you have the room where you enter. Normally you can enter to 3 or 4 rooms. It depends. When you go up, you enter to less amount of rooms. And then you have the patio. And these elements, you repeat it in each one of the 3 cores. And then all the dwellings, all of them, they have cross ventilation. Some of them because they face two facades and some others to the patio. This is the aggregation unit. Here you can begin to understand, the walls made with the air, the loading walls. This is an image from this room where you enter to the dwellings. We use lattices in order to give some intimicity to the dwellings and also to generate some movement of the air. And the important thing here is how to heat the house without any haptic system. So we use the winter garden strategy and also the greenhouse strategy. So each one, the relation of the rooms with the outside, it's all the time with winter gardens. And then we cover all the patios with this atrium that they work as green gardens. So this is the image. They are built with good light structure. Okay, so it captures the sun in the winter, and also, we also capture with the winter gardens into the and then the shape of the building, it's more compact because everything is close and in the winter, and also we don't have we have this envelope of isolation, so we don't have any thermal points, and we use a lot, like we are having the earth as the walls. We want to use a lot the inertia of all the materials. You see, this is an image of the winter gardens. It's social housing. All of them are going to be social housing. It's white because in summer we were very worried it got too hot, so that's why we decided to make a very clear the winter garden. This is from the inside and on the outside, with these glass curtains. And this is the simulation of the atrium, where we can see outside we have this 14 degrees, and we get up to 23 degrees up. So it's around 8 or 9 degrees over than the temperature we have outside. But the problem we have here is that all the heat, it's in the top of the atrium. That's why we place a fan in order not to stratificate all the heating. And, we have 21 degrees, it's 6 degrees over the outside without any active system. And this is the data. Here we can see, this is the temperature outside in the winters, in a week, in the standard winter week. So we go up to 15 degrees and down to 9 degrees. And inside the house, we have a constant line of 21 degrees without any active system. This is very flat. It's very constant because of the inertia, and it rises this temperature because of the winter gardens. But the main goal, the most difficult thing is to do this in the islands is for the summer, because we have very hot summers, very humid summers. So the atrium, we change it into a solar chimney. So we have the solar protection in the interior. So that means that it heats here, the air gets heater as everything is open. So all the heat, the air is going up. The heat air is going up. So it generates a movement of the air, even though there is no movement of the air outside. And also, as we open everything, the shape of the house, of the building, changes a lot. So all of this surface begins to dissipate the heat. And then we have all the cross ventilation and, the humidity, that the hygroscopicity of the earth, that it's able to regulate the humidity to put it down to this 50-60% that we talked at the beginning. So this is an image of the patio, with the lattices that give this privacy. And this is the simulation where we understand that, there's something interesting. We did the competition and all the slabs were made with concrete. And then we realized that we needed more inertia. And that's why we changed it to do them with concrete. So they were made with wood at the competition, sorry. But even though we did it with the more inertia we need, we know in summer, we don't have a flat line as we did in winter. That means that we should have put more inertia also, but I don't know how. But the point is that, we cannot put the thermometer, the temperature, we cannot put it down. We cannot, here we have 32 degrees, and here we have 23 degrees, and we have like a constant line around 26, 25 degrees. So this is the lower we can get. But the point is that we don't, if we want to rise the temperature low, to put it low, we should have put on the machine of carrier. So as we don't want to do that, we have to look for other strategies. So that's why movement of the earth on all the parameters that we were talking at the beginning are the ones that we are going to take into consideration. So as we have all the houses with this cross ventilation, and then we have this solar chimney, that, we place these openings, and this is a simulation of how, even though there is no movement of the air outside, we get this movement of the air around 2 meters per second. And you have to understand that it's half meter per second. You have a feeling of 1 degree less of your feeling, but the thermometer doesn't change. That's the important thing, okay? So to finish, you have to understand this is how the abacus that we were talking at the beginning, how it's when it's affected to the other parameters. So even though we have an air temperature of 29, we see the simulations we're talking about 26. So this is like the worst situation we can expect, and a speed of air of 1.5, even though our simulations were talking about 2 meters per second. The humidity, important, no? With the earth going down from the 80 to the 60, 56, and then wearing the proper clothing, that generates that even though being here, the green area moves to get the comfort. So we don't need to put the machines. That's the main goal. So in this case, we have this social space, the atrium acts as a social space for the building, but it also is the environmental solution for not having an active system. Another project here in Barcelona that we have already built, this is a project, all of them are social housing, they come from competition. When we did these competitions, we didn't know if we had to do a block that converts into a tower or a tower that had a block in the blower plans. So, but, as the south was coming from here, and this was the best facade, we realized that it should be a tower. So we have to consider openings in all the facades. If we've had the block, that would have meant that we wouldn't have a system that generates windows. It's very close to Lamina, okay? So this is the plan that we did. We used this idea of the svastika, no? So each time each room has these 2 orientations. So you have the cross ventilation, and you can make the capture. And then when we get to the tower, to the block, these 3 rooms, these 3 dwellings stays the same. These 3 are the same. And then appears this typology that it's a bit different because it incorporates the vacuum in order to generate the social space that we're talking about. So the important thing here, it's more this vacuum, it's not a very big building, it's around 17 meters. Normally, you don't expect to find a patio in these kinds of blocks. But, we make this patio in order to have this cross ventilation, and also was the opportunity to generate another atrium that can change the factor, the shape factor of the building in order that you capture on winter, you dissipate on summer, air enters from the north and comes from here. So you make a movement of the air that it's able to renovate all the air of the building. So these are the simulations. The interesting thing is that the facade that has more hours of sun is the roof. It's not any of the orientation. So here you see this is a scheme. We can see here the movement of the air, the idea of the atrium, and also this point that for us is very important to generate some social spaces in the middle of the building. So we have a social space in the entrance and also social space in the fifth plan where we change from the tower to the block. And finally, to enter into the roof, we have another social space. So this is the image of the atrium, the material using the brick. It's very important, again, because of the inertia. So this is a bioclimatic space, so we don't put any heating in the common areas, but we generate this space with this comfort because of this, using these materials with a lot of inertia. So, this is the first floor where the air enters and it gets out in the fifth floor through this opening. So it gets, in winter, it's closed, and in summer, it gets open, okay? So, this is the material. It's a brick burned with biomassa. It's a manual brick, okay? And, when you look the other way around, you see this social space, this double space. When you get this relation between the neighbors, you generate these spaces, where you get the entrance to the terrace. Then the importance of the curve, because for us it's the curve. It's something that doesn't belong to the patio, and it's something that it's going through there. So this use of the geometry in order not to make the patio only one piece. Okay. And this is another project also in Barcelona that we are building with the same strategy. Okay, in this case, it's senior. There are three buildings in one, and in fact there are four. But we have a parking, we have the housing for the refugees in the ground floor, and then we have rental housing and senior housing. And the competition, we had to do a building for each one of them. So I think we won the competition because we were the only ones that put one use on top on the other. So we make this a certification of the uses. Also because we wanted to use this strategy of the atrium of the green gardens in order to capture this energy to all the uses at the same time. And we had to have this social and this relation between the different uses. So this is how it works. So each one of them has a core. So we have one building in top of the other, so they are totally independent. They only connect with the fire staircase that we have at the end. So we have these common spaces. Again, the social space. It's 4 dwellings. We have these entrances, and you are going through these 5 patios that generate this idea of the enfilade. That here we also have the light, but we also will have the heat. And in the top, we have this very big green garden that covers and also generates some social spaces for the senior houses. Okay, this was the project, and now we are building. We have the ability to change it into wood truss. This is another render of the space. This is how, in the moment we were around 5 months ago, but and this is the final shape of the patio. We increases this because the orientation of the building is north that normally are facing only north. Actually, they have south, so that's why we increase it. The deepness of the patio in this place. And, this is again very similar of the idea of reducing the demand. But I want to show, how we like to work. We don't like, we have a very low budget to do this building. So what we do is to do these simulations, and in some moments we know that it makes no sense putting more insulation because all the demand, it comes from the glassing, So if we don't have the money to change the glass, then it doesn't make sense to put more money other places. So we constantly go to the limit of what we need. But the difference of this project in comparison to the two ones before, it's that in this case the social space is so big, so we use it as a heat recuperator, recuperador de calor. Well, it's, ¿cómo? Recovering heat. So it works as a recovering heat machine. So it works like a big machine. So all of the drawings, they take air, the interchange of the ventilation of the air. It doesn't come from the exterior, it comes from this space. So through infiltration, we have this renovation of the air, and we're able to put down, here is with the atrium, but without the renovation. So we have a very low demand, but it's much more low. It's 74% less, just using this strategy of the ventilation. Changing the strategy, when we want to be environmental but economic, our strategy is to reduce. So if we use less amount of everything, it will cost less and it will be more efficient. In this case, I'll explain the project of Cornellà. We use wood. This is the scheme of the competition of wood. We wanted to do that the crosses were structural, and I will explain how we developed that and how we realized that it was not the more sustainable way to do it. So this is in construction. The first thing to say is that one of the difficulties is the fire resistance of the wood. So there's two strategies. One is to allow the wood to be burned. So each centimeter allows you around 30 minutes extra. So we needed in this building this resistance of 90 minutes. So that means that if we want to expose the wood, we should increase 3 centimeters from the one that we needed from the structural requirements. And the other strategy that we can say, that's the one that we took in the slabs, that we let them expose. And the other strategy is to protect it, covering it with some boards. So each plaster board is around 30 minutes. So in this case, we use 2 layers of plaster boards of 15, and then 1 centimeter extra. So instead of 9 centimeters, the structural walls are 10 centimeters. And that's how we got to the 90 minutes of resistance. But the point is that as we had all the crosses, that was a very big problem, because we could make 3 extra centimeters of wood of each one of the faces exposed. So that means that each cross should increase 6 centimeters, or we have to cover with plasterboard, and that was a very high cost for the building. And also the relation of the surfaces, they were not working. So that's why we took the decision of changing this idea of the walls into pillars and glulam beams. So in this case, they have the fire resistance just because of their shape. They don't need to be increased to have this fire resistance. So and then an important issue here is the structural behavior. In this case, we were talking about this distance between these rooms, that they had this measurement of 360, and they were, if we make a board only with 2 supports, the deformation, it's around 6 millimeters. But if we make it in one piece and we compensate moments, no, and we have these 4 supports, it decreases into 3 millimeters, the half of the formation. And if we also add the cantilevers, we are able to put around 1 millimeter of deformation in the interior of the building. So like using this, that means that in the first situations, we needed more than 15 centimeters of CLT to do the boards, and we only needed 12 by compensating moments. So that is the thing that help us to build it with the 15 centimeters and have the 3 extra centimeters we needed to do the fire into the slabs. And this is, you see here, you see the cantilevers, you know. And again, with the pillars and the beams, we have the same, no? So the best thing is to have beams of all the length of the building, but that's something that is not possible because of the transport. So we have to make some joints, and making joints with wood, it's very difficult to make them hyperstatic. So they are always articulations because it's very difficult to do them. So the strategy is, well, if we only know how to build articulation and we want to compensate moments, where do we have to put the joint? So instead of putting joints into the supports, what we did is put the joints where the moment is 0. So that's 1/5 between the distance of the supports. And that's why we decided, we designed a piece of steel that allow the beams to spread into 2, and they are, you know, the beams measure 20 by 35 and 40 by 35. So that means that we have 2 beams of 20 that it's much easier to be built with the machine. And we allow the beam to pass, and then we have this final piece, so we avoid the compression of the pillars into the beam. And for me, this is the clue of this building, you know, this idea of allowing, no, the moments to be compensated. And here you see, this is the joint, no? It's very easy to imagine, you know, the bending diagram in the architecture. And you see the pillars, we have no holes, you know, the holes are the joints of the CLT panels, you know, the same place where all the installers, the facilities, the services go. It's the same place where the pillar is going through all the building. And, you know, this is the final plan, no? At the beginning for us, we were not sure it was better to do the crosses and this, but we realized when we saw this diagram, you know, in the competitions, we needed 0.50 cubic meters by square meter. And in the final versions, we needed 24 cubic meters by square meters. So it's less than the half. So we like to say that even though building with timber or with wood is sustainable, building with a half of the wood is more sustainable, you know? So this idea of reducing, you know, you are more cheaper, you can achieve the budget, but you also are more sustainable. Going back to the first project, the one of Ibiza, we like a lot to choose materials through their characteristics. In this case, you know, we look of the conductivity, also the density, and also the hygroscopicity. So you see, in this project, we wanted 2 things. We want inertia and we want hygroscopicity. So that's why, you know, the ones of more inertia are some way, maybe the bricks, some way the concrete is the best one. And then we have the earth, okay? The wood was not the best one with inertia because their density is very low. But when we see the hygroscopicity, you know, the best one is the earth, you know, because the earth is kind of the double of the wood, even though the wood is a very good one, and it's around 20 more capacity of regulating humidity than the concrete. So that's why we decided to use earth to do the building. the factory that that was building this, they used to have these very long pieces, 1 meter pieces, and they were very spectacular. It looks like a Thunter pavilion, but we were not sure of that because we had to do 43 dwellings. It was a very big building, and to put this in place, you need some extra machine and you cannot go as fast. So that's why we talk to them and we say, we have to do a very a small piece that you can handle with the hand. Even though it's not that spectacular, but what we wanted was not the how you see it, it's, how it behaves. So this is how we built it, you see all the workers, taking them with the hand, for us, this is the important thing, so this collaborative part. And, we built this labyrinth of walls, all of them made of earth. Then we covered them. It looks more like a cave. Then we took a decision because, in this country, we don't build very well. And, we, as another way of making the reduction thing is not adding more layers. So we wanted the earth to be exposed, but maybe the sound could go through the joints because we don't do very well joints. So that's why we plaster some clay and then we make this polishment of the clay. So we make sure that all the joints were totally closed. So without losing, without having to cover it with other materials. So that's, when you see it built, you see, the polishment, it also, they are very big houses. So you have some reflections that are very interesting through the polishing process. And again, here, there's something that for us is important because when you reduce all materials, what happens is sometimes you get a very raw space, no? So when we add, all the timber, all the wood of the slicing doors of the furniture, that helps to have some cooked. So it's like the raw and the cooked of Levi-Strauss. It's this equilibrium that for us is important. In order to have the earth, you need to have the wood. Okay. Well, this is images of. Here we see the winter garden we were talking at the beginning. Yeah, compressed earth blocks. Yeah, well, okay. You have some gravel, you have some sand, you join in everything with the clay, and then you put a bit of lime. So then you just make the compression and let them dry for 1 month or something like this. Then there's no coction, there's no energy involved. No, nothing, no seeming at all, nothing, zero. It was forbidden in the blocks. Okay. And also, all the electrification has to be exposed and these kinds of things. Okay. Well, here we see the way of making it. No, so you have a 20 centimeters wall in the partly walls that are the structural ones. So that's because, we have the density of these 2,000 kilos by cubic meter. So we needed around 300 kilos by square meter of wall in order to be able to solve it with only one material. No, if the weight is less, we need to put layers. So we didn't want to put layers. So that's why we make the wall of these 20 centimeters. But then the other walls, the ones that are for the traba, the ones that are for the wind, are only 10 centimeters ones. And then there was this subject that I talked at the beginning. No, we realized because of the demand that it was better to build it with concrete, the slab, than using the wood. That's why we were thinking, well, which is the way to be more sustainable using concrete? So we designed these beams. They are 20 by 10 centimeters beams. it's 80 centimeters. And we have this compressed layer of 5 centimeters. So you have 25 centimeters of a structural dimension, but the nice thing is that it's the equivalent of a slab of 10 centimeters. So it's less than the half, it's around 66% less than the structural one that you're using. So it's another way, so this concrete, it's 66 less emissions than a standard one because of using of geometry. And again, to do the pavement, we have to make a floating pavement in order you have here, the acoustic is the spring mass strategy. So to have the other mass and also to have this floating pavement, all we did is just to polish this concrete and not to add a layer to do the pavement. So here we see how we construct the slab, with these precast beams, And another good thing is, as we wanted to use the inertia, you have more surface of interchange. So that means that it works like a radiator in the other way around. We isolated everything with cork. There's no thermal breaches. And then we made a final finish with some lime plaster. And sometimes to do the stairs, we need to do some covering. So all of them are made with the clay boards over a good structure and with a mortar of clay, that it's also very good regulating humidity. And to do the covering, all the isolation, it comes from the Posidonia, and with working, not having, the slopes are made with the wood, not with the concrete, so it's very low concrete. And to do the exterior areas, we only use gravel, so everything infiltrates the water. And to do the separations, you use the gabions with some gravel. So everything is dry, and try to use stone and all natural materials. Here, the section showing how everything is constructed. But the good news are that even though we are building with concrete, our emissions are 423 kilos kilos of CO2 by square meter, and it's a reduction of 60% from the 1,000 of a conventional building. And then this is the strategy of reducing the emissions. In this case, the project of the senior houses, here we use a very similar strategy. It's a very big building. It's around 15,000 square meters. So we couldn't make the sectors. We had each plan should be a different sector. So at the beginning, we tried to do it with timber, but the timber doesn't behave very well to do this. So you have to cover it. So it was not a very good decision. So we tried to use the same strategy of the concrete, the optimized concrete with geometry. In this case, we did it with the prefabricated beams, and all the building, it's made with these elements, prefabricated elements, that they all come together, when we pour the in situ layer of 5 centimeters, all the beams and everything joins together. So again, normally a prefabricated structure is static, but we want it to be peristatic. So in this case, we don't use prefabrication in order to gain time. We use prefabrication in order to make it hyperstatic and also to use less amount of concrete. So it's an exercise of how to build with concrete in these moments where we know the emissions that we have with the concrete. So here you see all the slabs, and we do see, again, these spaces with these ceilings that we let them all expose, that are working like radiators. And and all the elements, the facade we increase the amount of elements of facade. All of them are structural, no? There are 25 by 25 pillars, each 3 meters. And the nice thing is that when you finish the structure, you already have the facade of the building. And another reflection about this idea of reducing, it's how to do the parking of the buildings. This is a building we did in Bon Pastor in Barcelona. And in this case, we were very worried, even though, you have this basement, but we didn't want to use ventilation systems. And we wanted to have a natural system. So that's why we generate some openings so air can enter, but also, light enters. And we like to have this reflection in the office because, maybe in 10, 20 years, with the autonomous cars, they wouldn't make no sense to park them under our buildings because they will be going around the city. So we are building something that in 20 years, we are sure it won't be necessary. That's why it's time we have to face a parking. We think, well, a parking, it's the use it will have now, but we have to think about the future use it will have. So here, that this is how it's working now, the parking, and this is how we think it will work in the future. You can enter through with the bike, park your bike, and then you have these locals, with the light at the end. And this is something that I will go through some projects that we take the same strategy. This is a case of a parking in Masnou, a building that social housing building we are building now. In this case, we have two floors of basement, and we want also to do the 2 floors with the natural ventilation. And we had to make some justifications, So we thought of how to enter the air in different situations. We make some simulations, And then, with this big open, that relates the both of the levels, We can see how air is moving, And, here its color, it's the oldness of the air inside the parking. So with these measurements, we were able to get the license to do this with the natural ventilation. And, in the second basement, we can plant this tree and have these new spaces. And this is the one of the tower block building. Again, you see, every time thinking of this entrance of the air, but also entrance for the light, for ensuring the future life of these spaces. And this is the one of the prefabricate. Well, the same. Okay. Okay, finishing. When you join the social and the economic sustainability, this idea of sharing, when generating these spaces, not only for one person, for the community. This also joins with this idea of the loneliness. We have some problems of loneliness. We have this pyramid population that it's totally inverted in Spain, but we also have loneliness with all the younger people. So that's why in some moments we think of this idea of making these intergenerational dwellings, and that's why this is the plan of the prefabricated building, the one of the seniors. In one of the plans, we convinced the mayors to do these intergeneration plans. We have, they share the kitchen, and we have an old person and a young person, they join together. So this is a thing that we're going to do in this project. It's something that we already done in Barcelona. This is a building for senior people, where this is a typology was very interesting because we were thinking of how to move around the house so you can move in both directions. So it's time you take one direction, your house changes. And the other interesting thing is that with movable doors, you can change, you can have all these situations in a 40 square meters house. Okay? And again, this idea of sharing, here, they share some facilities with the city. They share some spaces and the terraces, And here in the covering, they have these sharing spaces for the laundries and these kinds of things. Okay, this is the terraces, laundry spaces. They do this. This is a project we are working now in the office. It's a cooperative and for senior people. And here we will build it very similar with all we have learned with the project of Ibiza. And then the interesting thing is that when we solve this plan with conventional houses, we could only enter four dwellings, each one of 45 square meters. But then we make this proposal where instead of having 4 houses, we have 5 of them. Each one of them has 30 square meters, but they all share 50. So that means that each one will live in a 80 square meter house, and we can enter one more user. So that's the potential for us of sharing. No? So if you're able to share some part of your private space, you can win, and everybody can win, and everything can be more cheaper. So this is the economic with the social, no, and also in this case, no, because we are talking about all the age people, no, we this idea of the loneliness, when they share, you can fight against this loneliness. So this is the private spaces that they are also connected in order to take some cares if they need it. This is the spare that is shared, not these 50 square meters, and also the stairs. And then in the basement, they also share some spaces with all the neighbors. And, you know, they have these double spaces in order to get light into the basement. Okay, I'm finishing. Talk about this idea of about the adaptability of the project of Cornellà. We had this plot of 50 by 40 square meters with a patio of 15 by 25. It was the planning regulations. We didn't decide that. That's why we, in fact, we were nearly not to do the competition, but finally we decided to take a chance and make a very abstract enter. So we decided, well, we will divide this in equal rooms. So we won't draw drawings, we will draw rooms, no? So, but to make them all equal has some potentials, because when some things are equal, they're very easily interchangeable. So that gives you some flexibility. So in this case, we don't have room for the parents or for the children. They all measure the same. They can choose which one they decide. So you gain some flexibility, but also you have no hierarchy. So that's the new kinds of family we need. We don't have to have a hierarchy between the peoples. And so for us, it's important to be able to answer to the goals we need to do in our times. But also there was this reflections, which has to be the size of a room in order to work very well as a living room, as a bedroom. That's why we took this reference, you know, Marta, my partner, she made a PhD about the Japanese house, and we had this reference of the 8 tatami room. It measures 360 by 3. The nice thing is that in Japan, they don't call the rooms by their use because they change the use during the day. So they call them by the size. So the size is related to our bodies. So each one of a tatami, it's the measurement of a person. So it's a room for 8 persons. And also, you know, we found out that one of the versions of the kitchen of Frankfurt of Grete Litzowski measures 360 by 350, and La Petite Cabanon was measuring 366 and 366, and I think a pavilion over there also measures something like this. So we had this matrix of spaces where we can put in the most flexible room we knew, the most technical room we knew, and the room of thinking of Le Corbusier. So at this point, we knew that maybe in the central parts we'll place kitchens and bathrooms. We make all of them with cross ventilation. Sorry, and then we have this matrix no? Where, here you enter through a port, you enter here. But the nice thing is that it's very difficult to understand which is the limit between the users and which is the limit between the private and the public. And for us, this is important because shows this idea of indeterminacy that we have to have in these new situations, okay? But actually, it works very easily. So here you have the lift, the stairs. So you get into this room. You can enter into 3 rooms, 3 dwellings, and then you have this small corridor, and you can enter 2 more dwellings through the terrace. Okay, and there are 6 module rooms. 6 modules is 3 rooms, 3 bedrooms, and the potential thing here you see the stair. This is the common areas. Okay, this is the entrance of one of the houses. This is from inside the house, and the nice thing is that you don't see one space of 360 by 360, you see one through another because the openings are wider than the 80 standard centimeters. They are 1.60 m, 1.80 m, in order to have this porosity between the spaces. No? So, and this idea that you see, this is a room, this is a bedroom, but the light comes from the openings from the bedroom. And the importance of the corners, even though they are not structural, we build them because they help us to put all the furniture. And this idea that even though you are free in the kitchen, but you can see 4 of the spaces in one point of view. When you go up, you have some sharing space. And to finish, I would like to read this sentence that it's from Eduardo Chillida that says, always never different, but never always the same. That's something that we like to do in all our projects. Thank you very much.
Thank you, Jose. Fantastic lecture. Where is my camera? Okay. So, okay, we are going to have only 2 questions, one from the people online and the other from the people here. So if anyone wants to do a question that is online, please write into the chat. And but then I am looking for a question here. Okay. Okay, we are in the typical situation. Okay, we share the question.
So maybe it's like a yes or no question to you. Do you think there is an ideal size of a unit? Do you think it exists of a unit of a building?
Well, we are very happy with the 360 by 360. In fact, it's 13 square meters. And then when we use the 3x4 in Ibiza, that it's 12 square meter, it's not the same. It's better, the one of 360. I don't know why.
I like the project where you use the CSCB blocks, which is coherent with our project also, which we showed. So I was just wondering if it is viable and a good material to use in the real life in modern cities.
Well, okay, there is Minke is the father of all these kinds of this. They have many books about the compressed earth blocks and the ram earth. Gerard Minke, it's the best reference I can give you.
Good. So finally, we had only 2 questions in presence, no questions online. Thank you very much, Jose. This is your home, and thank you guys.